In this lesson, we're going to actually go through the 8 steps of hypothesis testing for what are referred to as independent groups. Now, look at that term, independent groups. The thing that I want you to remember is that when we're talking about independent groups of people, the implication there is that someone that is in the study cannot be in both groups. So probably one of the easiest examples of that is a study if we were looking at differences in gender. So we might have the group of males and the group of females and looking at, let's say, differences in attitude towards something. So you can't be in both groups. You're either male or you're female. The example that we're going to look at here is actually looking at the effects of scented paper on memory. And so what a researcher did was to get a group of people together, and he divided them into a group who actually, when they were trying to read a story and remember factual information about the story, they had the story written on scented paper, and the other group just had regular paper. And so it would not make sense to have any one person be a member of both of those groups. So independent sample t-tests mean that people cannot be in both groups. All right, so let's take a look at what you see in front of you. These are the 8 steps that are outlined for you, and we'll just start at number 1. Number 1, again, is to state the null and alternative hypothesis. The null in symbols is H sub O colon. Mu sub scented is equal to mu sub no scented. So SC is scented, NOSC is not no scent. The alternative here, again, we're going to write this in terms of our Roman letters. So H sub A colon, X bar scented, not equal to X bar no scent. And I'll give you a moment. I'll tell you the answer, but not right now. What is the form of that alternative? What type of alternative have we now written, and how many tails are we going to be using? One-tailed or two-tailed? So hopefully you notice by looking at that you are writing a non-directional alternative hypothesis, and that is going to result in a two-tailed test. Step number 2 is to select your level of significance, or your alpha level, or the level of risk that you're willing to take. And for this example, we're going to be working at the 0.05 level, which means that 5 times out of 100 we're willing to accept that we may make the wrong decision. 5 times out of 100, any differences that we see in our means could have happened by chance. Step number 3 is to determine the type of test that we're using. And based on the information that I've given you, the fact that the members of the study can't be in the scented group and the non-scented group, that results in us actually using an independent samples t-test. Step number 4, in a few moments we're going to be calculating the test statistic. And you see some of the things that we'll be identifying and calculating. SC is simply the variation in the scented group. SSNOSC is the variation in the non-scented group. SP squared is going to be something called the pooled variance. S sub x bar 1 minus x bar 2, that's the next symbol there that you see, is something called the standard error of the difference between means. And we'll be talking about that when we get into the math. T sub O is simply our T observed. The formula for T observed is x bar 1 minus x bar 2 divided by S sub x bar 1 minus x bar 2. The top of that is pretty simple, just the mean of the first sample, so we'll call that the mean of the scented group, minus the mean of the non-scented group, or x bar 2, again divided by something called the standard error of the difference between means. So in the next page we'll examine that. Step number 5 is to determine t-critical. I actually have a separate lesson that's going to introduce you to that. Step number 6 is to compare t-observed to t-critical. Step number 7, make your decision. And then step number 8, interpret your results. So let's look at the next slide and start talking about how to make some of these calculations. What's nice about the data is basically down through us calculating s squared, s sub p squared, the pool variance, there's nothing in here that really should be something that's new to you. I went ahead, instead of using X's, I used labels for our scented group. So there's the scores for our scented group. You see a column of scores for the non-scented group. For both of those columns, we summed them up, and then we found the average score for both groups. So that shouldn't be anything that's surprising or super scary for you. Then I went ahead and squared each of those numbers. So x squared for the scented group, the 25 squared is 625, 23 squared, 529, and you can work your way down that column. And then I went ahead and added up the sum of x squared for you. And again, I left the parentheses off there, so if you want to add those, you can. But the sum of x squared for the scented group was the 4959. And then moving over to the non-scented group, the sum of x squared for that group was the 3534. So again, up at the top of the page, you could have done that work probably within the first week of this class. So there's nothing new or scary about any of that. Moving down to the middle of the page, the next thing that we're going to do is calculate the variation in each of the groups. And again, probably within about 2 weeks of this class, you could have done these calculations. So the sums of squares, or the variation in the scented group, is 198, and the variation, or the sums of squares, in the non-scented group is the 246.88. Now, we do have a new friend to meet here, and it is the SP squared. And SP squared stands for something called the pooled variance. A couple of things that I want to talk about related to this is that firstly, we do have some assumptions when we're doing independent samples t-testing. And the first assumption is homogeneity of variance. And that assumption means that we assume that the population variances are equal to each other. And so what we're going to do is estimate something called the pooled variance. Now, before we do that, I want you to think back to our discussion about the central limit theorem, and I want us to talk about something called a sampling distribution of differences between means. So when we were creating or talking about the central limit theorem, we took 1,000 samples, size 64. For each of those 1,000 samples, we calculated a mean. We did that again 1,000 times, and then we graphed those means in a frequency distribution and created a sampling distribution of means. And again, as you recall, the standard deviation of that was called the standard error of the mean, and we used that to estimate the population standard deviation. And so let's talk about the sampling distribution of differences between means. Again, we're going to use our 1,000 samples, so we take pairs of 1,000 samples. We calculate the mean of each pair, and then calculate the mean or the average difference score for each pair. So let me say that again. We're going to take 1,000 pairs of samples, calculate the mean of each pair, and then calculate the mean difference between each of those pairs. So we're going to calculate x bar 1 minus x bar 2 for each of those pairs. These mean differences are then plotted in a frequency distribution. And again, all of the information that we know about central limit theorem still holds true. And the standard deviation of that distribution is something called the standard error of the difference between means. S squared or SP squared, our pooled variance, is what we are going to use to estimate the standard error of the difference between the means. So the formula for that says take the variation in the scented group, add it to the variation in the non-scented group, and then divide it by the number of people in the scented group plus the number of people in the non-scented group minus 2. So let's say that again. Our pooled variance is the variation in the scented group plus the variation in the non-scented group divided by the number of people in the scented group plus the number of people in the non-scented group. So that's N sub SC plus N sub NOSC. Those two added together, and then subtract out 2. So for this data, it's just a matter of finding or bringing down the variation in scented, the variation in non-scented, and then recognizing that there were 9 people in each group. So 9 plus 9 minus 2, and we work our way all the way down that, and we find that for this set of data, the pool variance is 27.81. If you're interested in a kind of a definition or more of a description of pooled variance, a way to think about it is that SP squared is the average of the two sample variances. Think back to the first week or so of this class. How did we go from variation or sums of squares to variance? We took a sums of squares and divided it by n minus 1. So if you take a look at that formula, that's really all we're doing here. We're saying let's take the sums of squares in scented plus the sums of squares in non-scented, so we're combining those and dividing them by n minus 1. I just wrote the formula a little bit different, but another way of writing the denominator is the number of people in the scented group minus 1 plus the number of people in the non-scented group minus 1. So let me say that again. Another way of saying the denominator is n scented minus 1 plus n non-scented minus 1. And so it comes out to the same exact thing. So our pooled variance is just the average variance of both groups taken together. Now, to make it a little bit easier, maybe I should have done this from the very beginning. I'm going to use the SC is SS1, non-scented SS2, X bar SC XS1, excuse me, X bar SC is X bar 1, and X bar non-cent is X bar 2. Some of these subscripts can get long and a little bit difficult to kind of keep up with. So I think on this next page you're going to see the ones. All right, let's move on and calculate something called the standard error of difference between the means. So again, since we are dealing with samples here, we have to estimate that for our or from our two samples. So SS X bar 1 minus X bar 2 is an estimate of the standard error of the difference between means. And the way that you calculate that is by taking the square root of the pooled variance times 1 over n1 plus 1 over n2. And again, n1 is the number of people in the scented group, n2 is the number of people in the non-scented group. So We bring over our pooled variance that we previously calculated. There were 9 people in each group, so 1 over n1 is 0.11, 1 over n2 is 0.11. And again, now we're just it's just a matter of crunching the numbers and doing the math. And so we find out that the standard error of the difference between the means is, for this set of data, 2.47. And then lastly, we calculate our t observed, and our t observed is equal to x bar 1 minus x bar 2 divided by, and I see a mistake up there that I'm going to correct, but that should be s sub x bar 1 minus x bar 2. So disregard this, that s right there. Okay, so I should have just brought down s sub x bar 1 minus x bar 2. And so then, again, it's just a matter of doing the math, bringing the numbers down. So our t observed for this data is equal to the mean of the scented group minus the mean of the non-scented group divided by that standard error. And what we find here is that our t observed is equal to, for this set of data, 1.57. Now I want to pause just for a second and have you stop and look at that, because it's very much like a z-score. Remember, a z-score is just x minus x bar divided by the standard deviation. And if you can remember from a previous discussion, anytime we're talking about a standard error, that implies, or that is actually interpreted as a standard deviation. So again, it's very much like a z-score in that it's the difference between two scores at the top divided by some measure of standard deviation. So let's talk about how to interpret this now, and this will be the last slide here. And so our 6th step is to compare our t observed to our t critical. And again, you have seen this before in your link to the future, and what you're seeing here probably looks like a normal curve, and so unless I told you otherwise, you would assume that we were looking at a normal curve. The truth of the matter is that we are looking at something called a t-distribution. A t-distribution, here's some things you might want to jot down about it. A t-distribution has a mean of 0, and so we could put a vertical line there in the middle. Has a mean of 0, and it's in the middle. T-distribution is symmetric about the mean, and so that's why it does look exactly like a z-distribution. It has a variance greater than 1, but as the sample size increases, the variance approaches 1. The fourth thing that you need to know is that there are actually a family of t-distributions. And there's actually a t-distribution for every possible sample size. And then lastly, the t-distribution approaches a normal distribution as sample size increases. And we can point that out when we go in and look at trying to find our t-criticals. That'll be, again, another lesson. So what I've done for you is found those for this set of data. And notice I say what you need to find your critical value is your alpha, which in this case is 0.05. The number of tails, we wrote a non-directional alternative hypothesis, and then something called degrees of freedom. And we'll be talking about degrees of freedom when we actually get into the lesson about how to find t-critical. But suffice it to say now that our degrees of freedom is 16. And let me move back up to the previous slide. Actually, it's 2 up, because the degrees of freedom for an independent samples t-test is always going to be the denominator when you calculate pooled variance. So here there were 9 people in each group. So 9 plus 9 is 18, minus 2 is our 16. And so you probably need to put that in your old canoodle, that the degrees of freedom for an independent samples t-test is always the denominator in the formula for your pooled variance for that set of data. Okay? So again, we're going to be talking about how to look that up in a few minutes. But I did look that up for you, and so our T critical was plus and minus 2.120. The thing I want you to know about that is that if I were to ask you to not draw this picture, but just to tell me what is T critical, if it is a two-tailed test, be sure that you put the plus and minus on there, because that tells me that you know that you're doing a two-tailed test. Remember from a previous discussion that our critical values mark, or are the line in the sand, or mark the different regions of this distribution. In the middle of the distribution is our fail to reject region, and out in the tails on either end is our rejection region. And so our decision here is to compare T observed to T critical, and notice that our T observed is within between the two critical values, so it's between minus 2.12 and 2.12, so it's approximately right here. And so when it's in this area, we fail to reject. Now, let me stop and make a comment here. Stop and think about, what does the null hypothesis say? The null hypothesis says that there is no difference between the means. So the null hypothesis says there is no difference between the mean of the scented group and the mean of the unscented group. As researchers, we would really like to disprove that. We would really like to say, no, we found that there is a difference. But when T observed is in this region, we cannot say with certainty that there is, that is an incorrect statement. So we fail to reject the null hypothesis when our T observed is in between those two critical values. Now our decision is fail to reject, and then step number 8 is our conclusion. And so this is almost verbatim how you would need to write this up. Based on the data collected, there is no statistical difference in memory score when studying using scented paper versus when studying using unscented paper. And what I've done for you here is actually write this up in APA format. And so I'll talk about that in just a few minutes, but I want to jump back up here and say this first. I like for students to get in the habit of using the terminology based on the data collected, because sometimes, and you even read it in textbooks, if we had found a statistical difference, people like to think we proved something. And the reality is what you found is based on just your one study. So based on this data. And so that's why I like to have students start this out by saying based on the data collected. So let's jump down here. So remember, when we fail to reject the null, that means there is no statistical difference. And the way that you would write this up for APA is T, and that's telling the reader, if they were to see this in a journal, that you did a t-test. And it's underlined. If you were really typing this up, which is what you would do for APA, you would actually italicize that T. And then in parentheses, you tell the reader your degrees of freedom, which again for us is 16, because that is the N1 plus N2 minus 2. In this case, our T observed is 1.57. So the next thing is T observed, colon, and then you tell the reader what your p-value is. And again, it's underlined because if you were typing this, you would put it in italics. And in this case, we can't say that 5 times out of 100 the difference we observed could have happened by chance. We have to say that It may be as high as 10 or 15 times out of 100. The difference we saw could have happened by chance, and we're not willing to accept that 10 or 15 times out of 100 we could have made it a mistake. So what we have to say is that P is greater than 0.05. And again, that's related to our T observed falling within this rejection region. And so we failed to reject the null. We concluded that there is no difference in studying using scented paper versus unscented paper. Now at the bottom, what I did for you is give you an example of what if T observed had been 6.42. And what we'll do is come back up here, and a T observed of 6.02 would have been something way over here. So our decision there would have been to reject the null hypothesis. And then again, here's our write-up for that. So I'll just read it to you, make a few comments here and there. Based on the data collected, there is a statistical difference in memory when studying using scented versus when studying with unscented paper, comma, T, 16 degrees of freedom, our T observed was 6.42, colon, P less than 0.05. And this will make a little bit more sense probably after we talk about how to find these critical values. Once we make that decision, particularly when you do find statistical significance, it's typical to actually identify the nature of the difference. So the next sentence is the average memory score for studying with scented paper was 23. SD equals 4.97, and I believe I recall correctly, these are the actual numbers for the scented group. Continuing the sentence, while the average memory score for studying with unscented paper was 15.1, SD equals 5.56. And I believe what I did is just subtract something off the mean of the non-scented group. And so this is an example of how you would write this up if you had found statistical significance. Now before we finish this lesson, one of the things I wanted to talk about is kind of how or what makes a t-test work. So I'm going to move back up and actually look at that T formula again. And so let's look back at the first page. And you might want to jot a few notes down about this. The first thing that I want to say is we're really kind of almost answering the question of what leads your t-test to yield a low probability that the null hypothesis is correct. And the first thing we're going to talk about is the fact that the larger the sample that you use, the less likely that the difference between the two means was created by sampling errors. So I'll say that again. The larger the sample that you use, the less likely that the difference between the two means was created by sampling error. And hopefully that kind of makes sense. Larger samples has less sampling error than smaller ones. So if you use a larger sample when you're doing the t-test, you're more likely to have a situation where you have a low probability, or probability low enough to allow you to reject the null hypothesis than when the sample is small. The second thing let's talk about is the difference between the means. The larger the difference between the means, the less likely that the difference was created by sampling error. And so that kind of makes sense. Without going back to the last page, for the data that we collected, our T observed was 1.57 or something like that. That we failed to reject that. In the example that I gave you, that I made the numbers up, our T observed was 6 point something. Well, that 6 point something was a function of there being a greater difference between the means. So say that one more time. The larger the difference between the two means, the less likely that that difference was created by sampling error. Random sampling does tend to create many small differences, but few large ones. So that when you do find a large difference between the mean, the t-test is more likely to yield a probability low enough to allow you to reject the null hypothesis than when small differences between the means were observed. And then the last thing, and again this has to do with the denominator, the smaller the variance among the subjects, the less likely that the difference between the means was created by sampling error. And we'll say that again. The smaller the variance among the subjects, the less likely that the difference between the means was created by sampling error. Let's stop and think about the populations. Again, let's consider a population in which all people are identical. They look alike, think alike, speak alike, act alike. How many do you have to sample to get a good sample? Really only one, because they're all the same. Thus there would be no variation among the samples, and you wouldn't have any sampling error. So as variation increases, sampling errors are increasingly more likely to occur. All right, so the first one again, kind of what makes this test statistic work, not work, but when are you going to be more likely, if you will, to reject? Typically the larger the sample, typically the larger the difference between the means, and typically the smaller the variance among subjects.